So let's dive deeper into the concept of sequences, okay? You'll recall that a sequence was a list of numbers, and we discussed in the overview the concept of a limit, okay? And we'll make it more formal here. So we have a super important theorem here, which is going to allow us to frame the concept of limits of sequences as limits of functions, okay? Now, limits of functions we're really familiar with from Calculus 1, and so being able to frame the problem of limits of sequences in terms of functions is really convenient. So suppose f is a function such that at the integers, okay, so f could be a real function, okay, with the domain of the real numbers, but at the integers n, fn is equal to an, okay? In other words, this is an explicit formula for a sub n, okay? This is an explicit formula for a sub n, but outside of the integers, you would just have a regular x value. So, okay, we have that function for all positive integers n. If the limit of f of x equals L, so just in general along the real line, the limit of f of x is L, then the limit of this sequence is also L, where L here, may be plus or minus infinity, meaning it diverges, okay? So that's really important. It allows us, so as long as we could, find a function where at least at the integers, we get our sequence, then we could frame the problem as a limit of a function. And this other theorem is convenient because sometimes sequences could be framed in terms of other sequences. So assume that the sequences A and B have limits, capital A and B, respectively. Then the limit of the sum or difference of these two sequences is going to be A plus B or A minus B, okay? So minus corresponds to minus and plus corresponds to plus. So if you add two sequences together term by term, okay, so each term is added together. So the first term is added to the first terms are added of A is added to the first term of B. The second term of A is added. And so that generates a whole new sequence, right? And so the limit of that new sequence, A sub n plus B sub n, is going to be A plus B for the plus and likewise for the minus. What about taking the terms and just multiplying it by a constant? Well, then the limit of that new sequence C A sub n is just going to be C times A. What about multiplying the terms of the two sequences together? Well, their limit, the limit of that new sequence, is going to be A times B. And what about if you divide term by term? Then the limit will also be A over B, okay? Provided, of course, that B is not equal to 0, because we can't divide by 0. And so let's take a look at a concrete example. So determine the limits of the following sequences, okay? So we have these sequences. For A, we're going to choose f of x is equal to 3x cubed over x cubed plus 1. And that any integer, 1, 2, 3, 4, 5, whatever, any positive integer, then this function will give us the terms. And so, excellent. We found our function, which matches our sequence at the integers. So let's take the limit of that function. So taking the limit of this function, and again, we go back to the Calc 1 concept. So you just divide the numerator and denominator by x cubed, and you get this over here. And when you take x to infinity, this goes to 0, and you just get 3. So what does that tell us about the sequence? That its limit is 3 by the theorem above here, okay? Well, what about n to the 1 over n, okay? Well, if you take n to infinity, you get this indeterminate form, okay? And you might recall that whenever you're dealing with this indeterminate form, that you want to take the log okay, of the limit, and then exponentiate at the end. All right. So that's what we'll do. And notice here, I mean, up here, I wrote out f of x. I gave you that explicit x. But once we're comfortable with that concept that we're just taking the limit and, well, let's just treat n as the sort of real number. And, we won't do this sort of pretense of changing to x and going to 3. I mean, we're comfortable with the concept now. And so we don't have to write it out explicitly as x. And so we're going to let L be the limit of the log of n to the 1 over n. Again, we'll exponentiate at the end. So that's how we'll work with that indeterminate form. And if we do that, you could take out the 1 over n outside the natural log. And so you'll get 1 over n times natural log n. And now you have the indeterminate form infinity over infinity. And we use L'Hopital's rule for that. We take the derivative of top and bottom. And again, we're sort of just treating n as a real number here to avoid the pretense of using x. So we take the derivative of top and bottom, we get 0. And so the limit of the original, so the non-logarithm is going to be the exponential of the limit with the logarithm. So we'll get e to the L, e to the 0, and that's equal to 1. So let's discuss some of the common terminology that will come up with sequences and is very important. Okay. So a sequence is said to be increasing if if the subsequent term an plus 1 is strictly greater than the previous term an. Okay. So here's an example of that. Each term is strictly greater than the previous. So that's said. A sequence said to be increasing if that happens. A sequence said to be non-decreasing if an sub n plus 1 is greater than or equal to a sub n. Okay, so here's that, 1 is not strictly greater than the previous term, but it's equal to. And so this is called non-decreasing. You can get the next term being equal to the previous one, but never less than the previous one. That's called non-decreasing. A sequence said to be decreasing if an sub n plus 1 is strictly less than a sub n. So each subsequent term is strictly less than the previous. And here's an example of that. Non-decreasing if we allow equality as well. And so here's an example of that. This negative 2 is equal to the previous term, but that's fine because it's non-increasing. Okay. Monotonic. A sequence is said to be monotonic if it's either non-increasing or non-decreasing. Moves in one direction. Okay, so you could get equality to the previous term, but you're either increasing at that stage or decreasing or equal. Okay, and so if it's either non-increasing or non-decreasing, then we say that it's monotonic. A sequence is said to be bounded above if there is a number m such that a sub n is less than equal to m for all relevant values of n. Okay? And a sub n is said to be bounded below if there is a number n such that an is greater than or equal to this n for all relevant values of n. Okay? And if a of n is bounded above and bounded below, then we say that a sub n is a bounded sequence. And some of you may have been wondering, what is the relevant terms here? So I'll point out that with sequences, all right, if you're looking at the limit, and this is going to be one of the major focuses that we have, is that we're going to investigate the limits of sequences. Then what matters is the end behavior, okay? So taking out a finite number of terms from a sequence will not change the convergence of it, okay? We could set aside a finite number, and it doesn't matter how large that number is, 10 trillion. That's fine. Or 10 trillion times 10 trillion. That's also fine. But a finite number of terms are not going to change the convergence, not going to change that end behavior as n goes to infinity. Okay? So if, for example, if the first few terms of a sequence are really, really large, but the rest of them are sort of bounded by this m, then, we'll consider that the sequence is bounded above for that. We could consider it for that end behavior. I mean, we could also make m large enough to also encompass the finite number of terms. But that's what's meant by relevant there. And it's worth pointing out that end behavior is what matters the most. So a finite number of terms will never change the convergence or divergence of a sequence. And this brings us to a very important concept here, a very important theorem, the bounded monotonic sequence theorem. Okay, a bounded, and again, what does bounded mean? Bounded means it's bounded above and below. So there is some number m where each of the terms is less than or equal to term, less than or equal to that number, and some number n where each of the terms is greater than or equal to n. So bounded and monotonic, so it's either non-increasing or non-decreasing. Okay, it's flowing in one direction. Okay. So a bounded monotonic sequence converges. Okay, it has to converge. Okay, so monotonic. So for example, non-decreasing. Okay, you can think about this as sort of like increasing, right? With the equality. So if it flatlines and just keeps being equal to the previous term, well, then you're reaching a limit, right? But even if it's increasing, say we're looking at that increasing symbol there. So even if the sequence is increasing, but it's bounded above, okay, or it's a bounded sequence, then where is it going to go? So you see this 1, 2, 3, 4. Now, okay, this is increasing. It keeps increasing, or let's say non-decreasing 1, 1, 2, 2, 3, 3. And what if I just tell you that this sequence is bounded above by the number 5? Okay, it only has one way to go. It can only keep going up. Okay, so here you could keep repeating 3. That's fine. Then the limit is 3. But even if you don't keep repeating 3 and you just keep increasing, 4, 4.5, 4.7, 4, and it's bounded above, you can't go above 5, and you can't go backwards, you can't go back down, you can't go back down to 1. So you only got one way to go, and that's why such a sequence converges. You're going to have to approach a limit. There's just no choice, okay? So that's the topic of the bounded monotonic sequence, and it's super important. So let's look at an example. So we want to compare and contrast the behavior of these two sequences. Notice that the sequence b sub n has this extra alternating factor, this -1 to the n. Okay, this -1 for even n gives you a +1, and for odd n gives you -1. So it just causes alternation. So we want to show that this here is bounded and monotonic. So I'll take the derivative here, and again we're going on the pretense that this n is just like a real number. So when you take the derivative, you see that the derivative is strictly greater than 0 for n strictly greater than 0. Okay, and what does that mean? That means that this is increasing. Okay, a sub n is increasing, which also means that it's non-decreasing, which means that it's monotonic. Okay, increasing implies non-decreasing, but non-decreasing does not imply increasing. Okay, so increasing, so it's non-decreasing. Basically, it's monotonic. So if it's increasing, it's monotonic. Okay, and on the other hand, notice that an upper bound, and you could just glean this from the form here, no matter how large n gets, this is just going to be one integer greater than the numerator, and so it's always less than 1. And if we plug in n equals 1, it's going to be greater than 1/2, so it's also bounded. Okay, a sub n is bounded and monotonic. What does that mean? That means that a sub n converges. Okay, and indeed, if we take the limit, we see that the limit is 1. It had to converge. Okay, and sometimes you'll find an upper bound. So in this example, it's increasing, so we're looking for an upper bound to prove the boundedness. we could get upper bound, but doesn't necessarily mean that it's going to converge to that upper bound, okay? So even here, for example, I was just kind of lazy and I said, well, this is always less than 5. I could still, from the monotonic sequence theorem, conclude that it converges, okay? Because it's still monotonic and bounded by, 5 in that case. Here, we actually can find the limit using the theorem on functions and find that it's 1. What about B sub n, okay? Well, here we got that extra oscillatory behavior there, okay? So we got that alternating term -1 to the n. And so what happens with B sub n is it keeps hopping, towards the end behavior between -1 and 1, okay? So odd terms will approach -1, and even terms will approach 1. And so B sub n, the sequence B diverges, okay? It does not settle on either 1 or -1. It keeps oscillating. Well, let's take a look at a special type of sequence called the geometric sequence. Geometric sequences have the property that each term is obtained by multiplying the previous term by a fixed constant called the ratio. So basically they have the form r to the power n, because we're multiplying by the ratio, each term is multiplied by, takes the previous term and multiplies it by r, or a rn, where a does not equal 0 and is a real number, and r is a real number, okay? A can be this sort of fixed factor in the sequence, okay? Let's take a look at this theorem. Let r be a real number, then the limit of r to the power n is 0 if the absolute value of r is strictly less than 1. You could see why that's happening, right? Why it would be 0. So if it's at 1/2 and you keep multiplying by half, so you start with a half times another half, that's a fourth, times another half times an eighth. So if it's strictly less than 1, then r raised to the power n, as n goes to infinity, will go to 0. The fraction keeps decreasing. If r is equal to 1, then you're getting 1 times 1 times 1 times 1 times 1, and so you're just staying at 1 there. On the other hand, if r is less than -1, okay, then the terms will grow without bound. If r is equal to -1, you're getting -1 times negative, then the next term is -1 times -1, or 1, and then the third term is going to be -1 times -1, negative. So you'll get that oscillatory behavior between -1 and 1, and you don't really settle down on a term, and so the limit does not exist if r is less than or equal to -1, or r is strictly greater than 1. R strictly greater than 1 means the limit will grow without bound, right? So if you have 2, for example, then you keep doubling. If r is strictly greater than 0, then r raised to the power n is a monotonic sequence, okay? It will, in this case, either keep increasing or decreasing, okay? But it is a monotonic sequence. If r is strictly less than 0, then rn oscillates, okay? So we don't get that monotonic behavior. Determine the limits of a sub n, which is given with this explicit formula there, and b sub n. So for a sub n, notice we're going to take advantage of the theorem that the sum and difference of different sequences you could basically find the limits individually. Okay, so we're going to take advantage of that and distribute the limit, if you want to think about it that way, over these two. So now we're treating these as two different sequences, and we're going to take the limit of each one. Well, here we get this r is equal to 0.6, and so that's strictly less than 1, so this 0 as n goes to infinity. Here r is equal to 1/3, and as n goes to, and again, that's strictly less than 1, and so this limit is 0. What about for b? What we're going to do is separate that 1/2n factor, okay? So we have this 1/2 raised to the power n, and there r is 1/2, and so this would go to 0, right? But here we have this other sequence, and we're going to take advantage of the fact that we could sort of distribute over a product, okay? So the product and limit commute, okay? That's taking advantage of this part of the theorem. And what we'll have is 0 there, and this is bounded, so you'll get 2/3. Thankfully, we didn't go to a indeterminate form, so we didn't have to use L'Hopital's rule. But there we'll then get 0 times 2/3. And and notice here that we could have multiplied top and bottom by 1 over n squared and taken that limit. You'll get 2/3. And so that's 0, okay, with taking advantage of the theorem above. Well, here's another super important theorem, the squeeze theorem, okay? So many of us have run into the squeeze theorem for functions. Well, you could frame sequences as functions along the integers, so it's no surprise that we get a squeeze theorem for sequences. So let A, B, and C be these sequences, with B squeezed between AN and CN. So CN is, each term of BN is less than or equal to the C sub n. So B sub n, so the nth term is less than or equal to the nth of B is less than or equal to the nth term of C, and greater than or equal to the nth term of A. So you're doing this term by term. For all integers n greater than some index n. Okay, and again, what does this some index n mean? It means that, maybe the first few trillion terms can't be squeezed between these two sequences, but after a trillion they can't. Well, that's fine, because what matters is the n behavior. We're going to n equals, and we're going to n as n goes to infinity, right? And so the first finite terms, no matter how large, it does not matter. So for some index n, so after some very large number, if need be, then if the limit of an is equal to the limit of cn is equal to L, so if these two sequences have the same limit of L, then B, which is squeezed between these two, also has the limit L, okay? And so let's look at a concrete example here. Find the limit of the sequence B sub n cosine n over n squared plus 1. Now again, cosine n, you'll expect some oscillatory behavior, but what do we know about cosine n? Well, cosine n, no matter what it is going to be greater than or equal to minus 1, right? It attains that value at cosine of pi. And it's going to be less than 1. It attains that value at 0. So cosine this is true of the cosine function. So we're going to try to squeeze. So we'll divide by n squared plus 1, and we'll be able to squeeze B sub n between an and cn, okay? So, this basically tells us here that this is true. Okay? And so, all right, we did it. We squeezed B sub n between two functions that, two sequences that we do have a grasp on. And the limit of those sequences, A sub n and C sub n, they're equal and they're 0, right? This approaches 0 as n goes to infinity, and so does that. And so by the squeeze theorem, this sequence B sub n also has the limit of 0. Now, it's really important to get a sort of intuition on which functions grow larger than other functions, okay? So the following sequence are ordered according to increasing growth rates as n goes to infinity. That is, if A sub n appears before B sub n in the list, okay, so this, for example, appears before that, then the limit of A sub n over B sub n is 0. So the limit of this natural log Qn over Np is 0, and the limit of B sub n over A sub n is infinity. Okay, and what that's telling you is that as you move to the right, these terms grow faster than the terms to the left. Okay, so what does this say, for example? This tells you that a polynomial, okay, regardless of what power the polynomial is, mind you, is always going to grow faster than a power of a natural log. Okay, so this is a natural log of n raised to the power q. P, Q, R, S are any real numbers, and B is strictly greater than 1 here. Okay, so polynomials always grow faster than powers of log, regardless of what polynomial. Polynomial times a log, regardless of what power of log, will always grow faster than the polynomial. A polynomial with S, even if S is slightly more than P, will grow faster than that same NP times a log, regardless of what R is. Okay, so any power, you can, and again, you could think about NP plus S is equal to NP times NS. Okay, so what this is telling you is that term will grow faster than NP times natural log of N R, regardless, even if R was much greater than S. Okay, it doesn't matter. Okay, and this is an exponential now, so B raised to the power N. Exponentials grow faster than polynomials. Factorials grow faster than exponentials, and exponentials raised to exponentials grow faster than factorials. Okay, so I'll remind you here that n factorial is equal to n times n minus 1 times n minus 2 dot 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 to 1. Okay, to 2 times 1. Okay, so that's what the factorial is. Factorials grow faster than exponentials, and then this beast here is n raised to the power n, and that grows even faster than exponentials. So take a look at this example. So we have natural log of n raised to the power of 10 over 10 to the negative 5 times n. Well, this denominator is a polynomial. N is raised to the power 1 here, and this natural log, even with n being raised to the power of 10, you could just take that 10 and move it out. Well, this natural log, regardless of what power of the natural log, and here the natural log is just raised to 1, and you have an n to raised to the power of 10, are always grow more slowly than polynomials. So this is 0. Well, what about this guy? Here we have this basic form. Here we have p is equal to 8 here, and natural log of n, r is equal to 1. Well, here we have 8 and 8.001, and so this is like taking, p equals 8 and s equal to 0.001. Up here, r is equal to 1. Regardless of r being greater than s, doesn't matter. That little extra s was, no matter how far we take the zeros, as long as it's finite, it's just enough to make that limit go to 0. Okay? And pay attention to the fact that if n was just 8, then we would have, this would dominate. So this would go to infinity basically if we did not have that s there. Finally, let's look at this factorial over n factorial over the exponential. Well, here's an exponential, b equals 10 there. And we have that factorial. Factorial always grows faster than exponential. And so we have that infinity. Okay, exponential with a fixed base. This is an exponential with a not fixed base. Okay, so the base itself even grows. Okay. So, and I'll write that note here that n to the 8th natural log of n over n to the 8th, that sequence go to infinity there, okay? And you could actually see that the n to the 8ths would cancel, and you'll end up with just a natural log. So that should be going to infinity there, okay? And let's look at the formal definition of limit of sequences, okay? Here we're gonna, bust out our epsilon knowledge there, and so this is a formal way to prove that a limit exists. So if we have this sequence, it has unique limit L. What does that mean? Formally, if given any epsilon greater than 0, any epsilon whatsoever, it's possible to find a positive integer n, depending only on epsilon, so n can depend on epsilon, such that a sub n minus L is strictly less than epsilon whenever n is greater than that positive integer capital N. Okay, so this is just telling you that if n gets very large, larger than this capital N, then all the subsequent terms will be less than that epsilon. And you could do this for any epsilon. So you could take epsilon as small as you want, okay, as it approaches 0, and you'll always be able to find some integer capital N such that all subsequent terms are sufficiently close to that limit. And we'll take a quick example there with the formal definition. So we know that the limit of n over n minus 1 is equal to 1. We know that from that functions theorem, that we could basically treat these as functions. Well, let's frame this in terms of the epsilon. So the limit is 1, and we want to show that with the epsilon definition. So we'll have a sub n minus 1 is a sub n is n over n minus 1, okay? And that's going to be equal to 1 over n minus 1, okay? And we're going to impose that difference is less than epsilon, okay? And now the goal is to see how large n has to be if this is true, okay? And so we'll take the reciprocal, which flips the inequality, and move that 1 to the other side, and we get that n needs to be strictly greater than 1 over epsilon plus 1. And so we'll take that capital N to equal this. So remember, n depends on epsilon. So if you want all your terms to be less than 0.00001 difference from 1, well, you'll have to just ensure that the terms that you're looking at are greater than 1 over that small epsilon plus 1, okay? And so this shows us that we can always find, no matter how small epsilon gets, no matter how much we want the limit to be close to the terms, we could always find a number n such that all subsequent terms past that n will be that close to the limit.